Good day everyone, today we will presenting a case study on 2015 Tianjin port explosion, a major industrial chemical accident that occurred in Tianjin, China. This incident gained worldwide attention due to its devastating impact on human lives, properties and the environment. Through this presentation, we will examine the causes of the accidents, the hazards involved, its consequences and the importance of effective chemical safety and health management in preventing similar disasters in future. The Tianjin port explosion occurred on 12 August 2015 at a hazardous chemical warehouse located in Tianjin, China. The incident involved a series of powerful explosions that were triggered by chemicals stored at the facility. The explosion caused widespread destructions across the surrounding area, resulting in numerous fatalities, injuries, and extensive property damage. The blast was so powerful that it was felt several kilometers away from the site. This strategy is considered one of the deadliest industrial chemical accidents in the modern history. It served as important reminders of the risks associated with hazardous chemical storage and highlight the needs for strict safety regulation, proper risk management, and effective emergency response system. To better understand the incident, it is important to look at the background of the incidents. The explosion took place at Tianjin port, one of the largest and busiest ports in China, which handles a significant volume of cargo and industrial materials every year. So the warehouse involved was operated by Ruhai International Logistics, a company responsible for storing and handling hazardous chemicals. Before the accident occurred, the facilities contained large quantities of dangerous substances, including ammonium nitrate and nitrocellulose. These chemicals can become highly unstable and pose serious risks if they are not stored and managed properly. Following the incident, investigation revealed severe safety and regulatory violations, including improper storage practice and inadequate safety measures. These findings suggested that weakness in chemical safety management played a major role in contributing to the disasters.
Okay, so before we understand how the explosion happened, let's first look at the hazardous chemicals stored in the warehouse and why they were so dangerous. The first chemical is nitrocellulose. It is highly flammable, which means it can ignite and burn very quickly. During the Tianjin incident, nitrocellulose is believed to have contributed to the initial fire, producing a large amount of heat that allowed the fire to spread rapidly. The second chemical is ammonium nitrate. Its main property is that it is a strong oxidizer. Although it does not burn by itself, it supplies the oxygen to a fire, making the flames much more intense. And when exposed to very high temperature, ammonium nitrate can decompose violently and explode. This is believed to be the main cause of the massive second explosion. Next are potassium nitrate and sodium nitrate. Both are also strong oxidizers. Their role was to release oxygen when heated, and which intensified the fire and increased the temperature inside the warehouse. This created the conditions needed for the ammonium nitrate to explode. Another important chemical is calcium carbide. It is highly reactive with water, and when firefighters use water to extinguish the fire, calcium carbide reacted with the water and produced acetylene gas, which is extremely flammable. Instead of putting out the fire, this reaction made the fire even worse. The warehouse also contains sodium cyanide, which is highly toxic. Although it did not cause the explosion, it became a serious hazard after the blast because it could contaminate the surrounding environment and pose a health risk to rescue workers and nearby communities. Finally, there was toluene diisocyanate, or TDI. It is a volatile and toxic chemical that can release harmful gases when heated or burned. During the fire, it likely contributed to the release of toxic smoke, increasing the health risk for firefighters and people living nearby. Overall, each chemical had different hazardous properties. However, when they were stored together without proper safety controls, they created a chain of events that led to the one of the deadliest industrial explosion in history. Next, this slide shows the chemical structures, formulas, and industrial uses of the chemicals involved. Starting with nitrocellulose, it has the chemical formula on the slide, and it is commonly used in paints, coatings, lacquers, varnishes, and propellants because it can burn rapidly. Next is ammonium nitrate with the chemical formula of NH4NO3. It is mainly used as an agricultural fertilizer and also in mining and quarry blasting due to its oxidizing properties. Potassium nitrate or KNO3 is widely used in fertilizers, fireworks, and rocket propellants because it can supply the oxygen during the combustion. Similarly, sodium nitrate with the formula of NaNO3 is used in fertilizer production, glass manufacturing, and the production of explosives. Calcium carbide or CaC2 is mainly used to produce acetylene gas for oxyacetylene welding and steel manufacturing. Next is sodium cyanide with the formula of NaCN, which is commonly used in gold and silver extraction, electroplating, and metal treatment. Lastly, toluene diisocyanide or TDI has the formula of C9H6N2O2. It is widely used to manufacture polyurethane foam found in cushions, mattresses, automotive seats, and insulation materials. Although these chemicals have many important industrial applications, they must be handled and stored properly because they can become extremely dangerous under unsafe conditions. Now, let's discuss the chemical reaction that contributed to the Tianjin explosion. So the first reaction involved calcium carbide. When firefighters sprayed water onto the fire, calcium carbide reacted with water according to this equation. CaC2 plus 2H2O produces C2H2 and calcium hydroxide. This reaction produces acetylene gas, which is highly flammable. Instead of extinguishing the fire, the water unintentionally made the fire more intense. The second reaction involved ammonium nitrate. As the warehouse temperature increased, ammonium nitrate decomposed rapidly, releasing large amounts of heat and gases. This decomposition is believed to be the main cause of the massive explosion because it generated enormous pressure within a very short time. The third reaction is the decomposition of potassium nitrate. When heated, potassium nitrate releases oxygen, and this oxygen acted as an oxidizer and allowed the fire to spread more rapidly and burn more intensely. Next, the fourth reaction involves sodium nitrate. Like potassium nitrate, sodium nitrate also decomposes when heated and releases oxygen, further increasing the intensity of the fire. Next is the combustion of nitrocellulose. Because nitrocellulose is highly flammable, it burns rapidly and releases a large amount of heat, and this heat helps spread the fire throughout the warehouse and increase the temperature of the surrounding chemicals. Finally, although sodium cyanide did not directly cause the explosion, it created another serious hazard. If sodium cyanide comes into contact with an acid, it produces hydrogen cyanide gas, which is extremely toxic and can be fatal even at very low concentration. In summary, the Tianjin port explosion was not caused by a single chemical reaction. Instead, it resulted from a chain of reactions involving flammable materials, oxidizers, and water-reactive chemicals. So these reactions, combined with improper storage and poor safety management, eventually led to one of the largest industrial explosions in history.
Now, I will explain the STS analysis for two chemicals that involved in the port explosion. The first one is sodium cyanide. For its properties, sodium cyanide is a white crystalline solid that is highly soluble in water and its odorless or faint bitter element smell like. However, it reacts with water and acids to release highly toxic hydrogen cyanide gas. It has a melting point of about 564 degrees Celsius and a boiling point of 1496 degrees Celsius. In terms of hazards, sodium cyanide is fatal if swallowed, inhaled, or absorbed through the skin. It can also damage organs after repeated exposure. The STS labels it with the signal word danger, showing that it requires very careful handling. The GHS pictograms indicate acute toxicity, serious health hazards, environmental hazards, and it is also corrosive. In terms of toxicity, cyanide prevents cells from using oxygen by inhibiting the enzyme cytochrome oxidase. This causes cellular suffocation, leading to symptoms such as headache, dizziness, breathing difficulty, convulsions, coma, and even death. For the first aid measure, anyone exposed should be moved to fresh air immediately and administer oxygen if breathing is difficult. Contaminated clothing should be removed, and the affected skin or eyes should be rinsed with plenty of water, and urgent medical treatment is required. Finally, for handling and storage, sodium cyanide must be handled in a well-ventilated area while wearing appropriate personal protective equipment. It should be stored in a cool, dry place away from moisture, water, acids, and heat. Next is the STS analysis for calcium carbide. For its properties, calcium carbide is a dark gray to brown solid that is moisture sensitive. It reacts vigorously with water to produce acetylene gas, which is highly flammable and explosive. It has a melting point of 2,300 degrees Celsius. For hazard identification, it causes skin and eye irritation, may also irritate the respiratory system, and releases flammable gas when it comes into contact with water. Its GHS pictograms indicate flammable substances, corrosive effects, and irritant or harmful substances. The signal word is also danger. Regarding toxicity, exposure can cause skin and eye damage, coughing, breathing difficulties, and environmental pollutions due to the release of the acetylene gas. For the first aid measure, inhaled victims should be moved to fresh air, while affected skin or eyes should be rinsed thoroughly with water before seeking medical attention if irritation continues. Lastly, for handling and storage, calcium carbide should be kept dry, stored in tightly sealed containers, and protected from any contact with water to prevent the formation of explosive acetylene gas. Overall, the STS analysis shows that improper handling and storage of sodium cyanide and calcium carbide can lead to severe health hazards and major industrial disasters, as demonstrated by the Tianjin port explosion. Let's see how the port explosion will be viewed under Malaysia's SIMA 1996 regulations. First, let's look at the hazard inventory. The Tianjin warehouse stored around 700 tons of sodium cyanide, which is highly toxic chemical. Under SIMA, the threshold quantity is only 5 tons, meaning the amount stored was about 140 times above the legal limit. The warehouse also stored about 300 tons of calcium carbide, while the SIMA threshold is 200 tons, making it about 1.5 times above the limit. Because these hazardous chemicals exceeded the threshold quantities, the facility will be classified as a top-tier major hazard installation or MHI. Next, under legal violations and process failures, the company failed to notify the authorities that it was storing such large amounts of hazardous chemicals. In addition, it operated without a proper safety case, and there was poor chemical segregation and storage management, all of which would violate SIMA requirements. There were also serious emergency responses and communication lapses. Workers were not properly trained to deal with calcium carbide, so firefighters used water, which reacted with the chemical and made the explosion worse. The company also failed to provide accurate information to emergency responders and their nearby community about the hazardous chemicals on site. If this incident had occurred in Malaysia, the authorities could immediately shut down the facility, prosecute the company, and impose heavy fines or imprisonment under SIMA and the Occupational Safety and Health Act. This case clearly shows why strict compliance with SIMA is essential to prevent major industrial accidents.
Next, I will explain the regulation and legal requirements related to the chemical safety. In Malaysia, the Department of Occupational Safety and Health, or DOSH, enforces the Occupational Safety and Health Act 1994, also known as OSHA 1994. This act requires employers to ensure the safety, health and welfare of all workers in the workplace. Under this regulation, employers must identify hazardous chemicals and provide safety data sheets or SDS for every hazardous substances used. They are also required to conduct risk assessment to identify potential dangers and implement suitable control measures. In addition, employers must provide proper training to workers so they know how to handle chemical safety and respond appropriately during emergencies. Emergency response procedures such as evacuation plans, spill management should also be prepared to minimize accidents and injuries. Besides following regulations, proper storage and handling standards are also essential in preventing chemical accidents. First, incompatible chemicals should be stored separately because certain chemicals can react dangerously when mixed together. Second, proper ventilation, clear labeling and good inventory control are important to ensure chemicals are stored safely and can be easily identified. Third, temperature, humidity, and ignition sources must be carefully controlled because some chemicals are highly sensitive to heat or moisture and may catch fire or explode. In addition, regular inspections should be conducted to identify potential problems, and emergency preparedness plans should always be in place. Finally, hazardous chemical facilities should be maintained and adequate safety distance from public areas to reduce the impact of accident on surrounding communities. There are several important chemical safety regulations in Malaysia. The first is the Occupational Safety and Health Classification, Labeling and Safety Data Sheet of Hazardous Chemicals, Regulation 2013, also known as the Class Regulations. This regulation requires hazardous chemicals to be properly classified, labeled, and accompanied by safety data sheets. The second is the Usage Regulation 2000, which stands for the use and standards of exposure of chemicals hazardous to health regulation. This regulation focuses on controlling workers' exposure to hazardous chemicals and protecting their health. Malaysia also adopts the Globally Harmonized System, or also known as GHS. This system standardizes the classification and labeling of chemicals worldwide, making it easier for workers to understand the chemical hazards through common symbols and warning statements. This brings us to a critical central question of our investigation. Did the company comply with safety regulation? The answer is no. State Council investigation and independent audits concluded that Ruhai Logistics failed on almost every level to comply with basic chemical safety requirements. They were operating under a pattern of systematic non-compliance that turned their warehouse into a ticking time bomb. The 5 primary areas of failure identified by investigators. First is a hazardous chemical was stored far beyond approved limits. To put this in perspective, the site was authorized to handle safe, nominal volumes. Instead, investigators found over 3,000 tons of hazardous material back on site, including approximately 7,000 tons of highly toxic sodium cyanide. That is 70 times the legal limit. Second, incompatible chemicals were stored too close together. This was a fatal compounding factors. Extremely volatile substances like nitrocellulose, which spontaneously ignites when dry, were stored in direct proximity to oxidizing agents like ammonium nitrate. When the nitrocellulose caught fire, it immediately triggered the massive detonative chain reaction of the surrounding chemicals. Third, the warehouse was located illegally close to the residential areas. Chinese environmental and safety regulations strictly mandate a 1 kilometer buffer zone, that's about 3,200 feet between hazardous chemical storage and public spaces. Yet, there were 3 major residential communities and a rail transit station within that zone. The closest apartments were a mere 5,000 meters away. This is why the human casualty rate and residential damage was so catastrophically high. 4. Safety documentation and risk management were dangerously inadequate. When firefighters arrived on the scene to tackle the initial fire, there was no accurate, accessible manifest of what inside the containers. Because of this lack of documentation, first responders had no idea they were spraying water on chemicals that react violently with water. And finally, regulatory approval and supervision were severely insufficient. Ruhai Logistics actually operated illegally for months without a valid hazardous material license between their temporary permits expiration and its former renewal. Corruption, bribery, and weak local enforcement allowed this violation to go completely unchecked.
Next, I will discuss the possible failures in standard operating procedures or SOP that contribute to the Tianjin port explosions. First, there was improper storage of hazardous chemicals. The investigation found that nitrocellulose had lost its wetting agent due to damaged packaging and poor storage conditions. It allowed the wetting agent to evaporate. As a result, the nitrocellulose became dry and underwent spontaneous ignition, which started the first explosion. Few more incompatible hazardous chemicals were stored in close proximity, such as ammonium nitrate, which increased the likelihood of fire escalation and a major explosion. This caused the second explosion. Secondly, there was excessive storage of hazardous chemicals. The quantity of hazardous chemicals stored on site exceeded the permitted regulatory limits. For example, sodium cyanide was reportedly stored in quantities far exceeding the allowable limit, significantly increasing the potential consequence of an accident. Furthermore, the chemicals were stored in excessive and quantity amount within the warehouse, which increased the overall hazard level and complicated the emergency response effort during the incident. Lastly, there was inadequate emergency response planning. Firefighters were not fully informed about the hazard chemicals stored at the site because of insufficient documentation and communication between them. As a result, they were unaware of the potential dangers that chemicals cause when responding to the fire, which increased the number of casualties. Based on these SOP failures, several root causes can be identified. The first root cause was inadequate safety management and monitoring. The company failed to conduct effective inspections and monitoring activities, allowing unsafe storage conditions, damaged packaging, and excessive chemical inventories to remain uncorrected. For examples, regular monitoring was not carried out to ensure that wetting agent in nitrocellulose was maintained at safe level, allowing it to dry out and become highly flammable. The second root cause was violation of safety regulations. The investigation revealed illegal storage of hazardous chemicals, excessive storage quantities, improper segregation of incompatible chemicals, and failure to comply with hazardous chemicals management requirements. The third root cause was lack of effective risk assessment. The company failed to properly evaluate the hazard associated with storing large quantities of dangerous chemical together. As example, there is no safety data analysis and also chemical inventory list. As a result, the risk of fire escalation and a major explosion were underestimated. In conclusion, the Tianjin port explosion was not caused by a single mistake, but by multiple failures in chemical storage, safety management, regulatory compliance, and risk assessment, which ultimately led to this catastrophic accident.
Now, I'm going to discuss about the impact of the Tianjin port explosion. Let's start with the impact of this case to the people. The disaster resulted in 173 deaths, including 104 firefighters and 11 police officers who were responding to the emergency. These responders were among the first to arrive at the scene and were unfortunately caught in the massive explosion. Next, approximately 3,000 people received emergency medical treatment, while 798 people were hospitalized due to injuries of varying severity. Here are the several factors that contributed to the death and injuries. People were exposed to toxic smoke that lead to respiratory failure. Other than that, cyanide poisoning may be caused by the exposure of the sodium cyanide. Contact with hazardous chemicals can cause burn to the skin and eyes. The explosion also produces intense heat and release dangerous gases into the air that causes consciousness or death once inhaled. Other injuries included cuts, fractures, crush injuries, and trauma caused by the powerful blast wave, flying debris, shattered glass, and collapsing structures. Next, let's look at the impact on property. The explosion completely destroyed the warehouse facilities where hazardous chemicals were stored. The force of the blast was so powerful that it created a large crater and caused extensive damage throughout the area. Many nearby residential buildings, offices, and commercial properties suffered severe structural damage. Windows were shattered several kilometers away from the blast site, and some buildings experienced partial collapse. Critical infrastructure, including roads, utility system, and transportation facilities, was also damaged. This disruption affected daily activities and emergency response effort. The disaster resulted in significant economic losses that due to the destruction of facilities, clean-up operation, and reconstruction costs. Lastly, the explosion had serious environmental consequences. Large amount of hazardous chemicals were released into the environment, causing water and soil contamination around the blast site. Toxic substances mixed with water and runoff increased the risk of environmental pollution. Next, the explosion created a large toxic crater which collected contaminated water and chemical residues. This became a major concern during the clean-up process because of the potential risk to a nearby ecosystem and groundwater sources. The blast site itself remained hazardous due to the presence of chemical residues and contaminated debris, requiring extensive monitoring and remediation efforts. In addition, the fires and explosion released toxic gases, smoke, and particulate matter into the atmosphere, resulting in air pollution and posing health risks to both resident and emergency responders. Now, let's talk about the lesson learned and future recommendation from the Tianjin port explosion. One of the most important lessons from this disaster is that hazardous chemicals need to be stored safely and properly. This means using the right storage facilities, keeping the proper amount, and ensuring that chemicals that are not compatible are stored far apart. Companies and responsible parties must follow the safety rules that are already in place. These rules are made to protect people, property, and the environment. Ignoring or violating them can lead to serious consequences, as we saw in Tianjin. Regular inspection is also very important. It helps find problems early before they turn into accidents. Inspection should be done regularly and properly, not just on paper. Emergency personnel must have clear and accurate information about the chemicals stored in the area. This will help them respond quickly and safely during any emergency. In the future, stronger laws, better monitoring system, and improved emergency response training help in reducing the risk and prevent similar accidents from happening again.
In conclusion, the 2015 Tianjin port explosion was one of the major industrial accidents caused by unsafe storage and poor handling of hazardous chemicals. This explosion led to major loss of life, injuries, and damage. This case proved that failure in safety management and regulation might lead to serious consequences. Hence, this case teaches the importance of safety rules and management in preventing any incident from repeating in the future.